The other type of reactions that the enolates undergo is with halogens, iodine, bromine, or chlorine. The reaction can go either by acidic or basic medium. Basic mediums are always more reactive. This means that the halogen is going to replace all the alpha hydrogens. In the acidic medium, the halogen is going to replace just one alpha hydrogen. So this is the difference between acidic medium and basic medium. So you're going to end up replacing the alpha hydrogen with the halogen. But the question is, how reactive is your reaction medium? The reaction is going to proceed by substituting the alpha hydrogen by the halogen, depending on the halogen that you are using. So let's have an example over there before we go into the mechanism. Always look at the medium that you are working with. If it's an acidic medium, then in this case, the chlorine is going to replace just one alpha hydrogen. Same thing, bromine in presence of acetic acid. So this one is acetic acid. So this is an acidic medium again. So with acidic medium, the halogen is going to replace just one alpha hydrogen. This is another example in there. Bromine is going to replace just one alpha hydrogen. I have two more over here, but bromine is just going to replace just one. Now for the mechanism of the reaction, we are going to start like we started in the tautomerization in acidic medium. So we will be making the enol, and then from the enol, we are going to react it with the bromine. So the first step, you protonate the oxygen. Water is going to leave a double bond and add lone pairs to the oxygen. These two are resonance structures of each other. So the water can attack either this alpha hydrogen of this resonance structure or this alpha hydrogen. Both are going to be the same. And you're going to end up getting your enol form in this case. Now, once you have your enol form, then we're going to go ahead and add whatever we want to add to that. Here in this case, we are adding a bromine. So this is how the reaction is going to go in acidic medium. Notice that I'm not forming the enolate ion in this case. I can't because I don't have a basic medium. So all I'm forming here is the enol. And then resonance happens from the oxygen to the double bond, and the double bond opens up and picks up the bromine. So when it picks up the bromine is going to be on the alpha carbon. So here you go. This is going to be the alpha carbon in there. Any extra hydrogen will be picked by the base in the solution, either bromine Br minus or water, whatever that base that you pick, both are right, and you are going to end up getting your bromination at the alpha carbon. The reaction is not very reactive, so the reaction stops here after you brominate just one alpha hydrogen. The same reaction can happen in basic medium, but the difference here now, bromine is so reactive. This is a basic medium. So bromine is going to replace every single alpha hydrogen that is in the way. So here you're going to end up getting a more than one bromine on the alpha carbon. It's really hard to stop the reaction, with a bromine. So let's have an example, tautomerization in basic medium. So the base is going to come, take the alpha hydrogen, form the enolate. The enolate can undergo resonance in there, but I'm just stopping at the enolate because this is an obvious nucleophile. The negative charge is going to come now, attack the bromine, pick up the bromine in there. After it does that, because it's a basic medium, it's so hard to regulate the amount of the base that you have in the solution. So the base is there and the acidic hydrogen is there. So the base now is going to come again and take that acidic hydrogen, form the enolate again. and then the bromine is going to attack again. So you're going to end up getting a dibromo product at the alpha carbon. The reaction is going to stop here. Why? Because you alkylated both, or you replaced both alpha hydrogens, and you don't have any other alpha hydrogen to replace. So on this side over here, there is no alpha hydrogen. If there were alpha hydrogens, then the bromine is going to come to the side and replace every single one of them. But here there is none, so the reaction is going to stop. Let's have another example here. This is a methyl ketone. The methyl ketone, this is their methyl group. This is the alpha carbon, and the alpha carbon has 3 hydrogens in there. This is in basic medium only, and you're using excess of the base, whether it is in excess or not. Bases are always in excess. And if the base is in excess, then the halogen is going to be in excess as well. Okay. So we're going to locate our first alpha hydrogen in there. And the base is going to come, take that alpha hydrogen and make the enolate. We're going to do this 3 times. Every single time we are going to replace the halogen by a halogen. So that is going to be the enolate, and now I'm going to react it with the bromine. This is partial positive, partial negative. So that nucleophile is going to attack the electrophilic bromine, and the other bromine is going to leave. So you're going to end up brominating the first alpha hydrogen. So this is going to be a bromine, but you still have 2 more. So we're going to do again another base. The reaction is non-stop. So another base is going to come, take that hydrogen, alpha hydrogen, form the enolate. And once it forms the enolate, again, so here you go. This is a bromine. Your bromine is going to attack again. And this is going to be partial positive, partial negative. And you are going to brominate the second alpha hydrogen. Now we have our third one. Base is going to attack again. Take that alpha hydrogen, create the enolate. And then you're reacting this with the bromine. The enolate attacks the partial positive bromine, the other bromine leaves, and you're going to reach a point where all the alpha hydrogens, they are replaced by the halogen. So you have a bromine here, a bromine here, and another bromine in here. Well, this is a very good leaving group, by the way. So over here, notice that on both sides, you have no alpha hydrogen left. Medium is still basic. So now, because there is no other alpha hydrogen left, and still my medium is a base, now this is going to act as a nucleophile, not as a base now. So this is going to act as a nucleophile. Remember what we said, always the priority is the acid-base reaction. Once you don't have an acid-base reaction, then you're going to treat your base as a nucleophile, if it is a small one. So this one now is a nucleophile. So if it's a nucleophile, it's going to attack the electrophilic carbonyl. And you're going to end up having a partial positive charge over here. This is going to come, it's going to attack this carbon, form a negative charge on the oxygen. Okay, it's the same rules that we already discussed in chapter 18. So you're going to end up forming a negative charge on the oxygen. And you added your OH, and then you have your bromine. Let's take this carbon out, and the bromine, and the bromine. Okay. Now, this thing is not very stable because I do have an excellent leaving group. This is a CBr3 over here. It's a very good leaving group because it's a weak base when it leaves. So it's an excellent leaving group. I can simply do resonance, form a double bond back again, and allow this whole thing to leave. So when it leaves, This is what I'm going to end up forming. I'm going to end up forming my carbonyl, my OH, plus the CBr3 negative. This is going to be my leaving group in there. This is going to be a base. Always look at the medium that you are working with. Your medium is basic. It doesn't make sense to get the acid. So that base is going to come and it's going to take that acidic hydrogen and to form the carboxylate. So we're going to end up forming the carboxylate plus the bromoform precipitate. Okay. That precipitate is kind of like a brownish in color. And the color of the precipitate changes with changing the type of the halogen that you are working with. So if you're using iodine, it's going to be called iodoform now. It's going to be a yellow precipitate. This type of reaction we use in order to identify methyl ketones. Because methyl ketones, these are the only type of ketones in there that have 3 hydrogens next to the carbonyl. So the bromination in acidic medium is going to proceed by replacing all the alpha hydrogens in there and creating a precipitate. With this, I would know when you see the precipitate, you would know that you started with a methyl ketone. This is another example over here with iodine. It's proceeding exactly the same in there. And in the last step, the leaving group is going to come take the acidic hydrogen and you're going to form your iodoform. In this case, this is the yellow precipitate. And that yellow precipitate is an identification that you started with a methyl ketone. Always look at the medium that you are working with. If it's an acidic medium, then you are replacing just one alpha hydrogen with the bromine. So I can, for example, add a base. And the base here that I can add any base, but this is just an example, carbonate base, lithium carbonate. Or I can add a pyridine. Both of these are bases. So what does the base do? The base here does elimination. So the base is going to come, take the beta hydrogen, form a double bond, the bromine is going to leave. So this is how you make the alpha beta unsaturated ketone. And refer to chapter 18, please. We studied multiple reactions on the beta carbon. When you are using weak nucleophiles, these are going to attack the beta carbon, form the enolate, and then you are going to protonate this enolate by a solvent in order to get to your product. Let's have another example. If we are starting with this ester, so you have an oxygen here, 2 carbons in there, and then a carbonyl, okay? And you are reacting this with sodium ethoxide in presence of ethanol. This is a polar protic solvent. It's going to be on the most substituted alpha hydrogen. And then the second step, I am using an alkyl halide. I do have here 2 types of alpha hydrogens. I have an alpha hydrogen here, okay? These 2 are the same. And then I do have an alpha hydrogen over here, okay? The ones in red are the most acidic. These ones are the most acidic because these are the ones that are next to a ketone. These are next to an ester. Check their pKa's. These ones are more acidic. So now the base and these bases, they are going to replace just one of these alpha hydrogens, not both of them. So this is going to be the alpha carbon, form the enolate. Once you form the enolate, so here you go, always draw your enolate in there. So you're going to form your enolate. You still have a hydrogen over here. This is a double bond O. And then after this, we're going to use the second step in the reaction. This is going to be my iodine. So this is going to come, attack the carbon, iodine is going to leave. So all what I did over here is a simple alkylation. So I am going to form my two carbons. I added two carbons in there, carbon 1, carbon 2. Here you go, and this is going to be my carbonyl, a carbonyl. Now, let's say, for example, if I want to do hydrolysis, in acidic medium in there. So hydrolysis with acidic medium means that I am going to break down the ester bond. Break down the ester bond, add an OH to this carbonyl and a hydrogen to this oxygen. Because with hydrolysis, you're going to end up getting a carboxylic acid and an alcohol. So here you go. This is going to be your final product after the hydrolysis in the acidic medium. This is going to be an OH, and here you're going to have an OH as well.